Good afternoon. Today we're going to be talking about section 3.5, derivatives of trigonometric functions. And we remember our trigonometric functions. We've got sine and cosine, and from that all others are made. So the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. There's not really a cute, funky rhyme to remember any of this. You just have to memorize it. So let's do a quick example. Calculate dy dx for y equals sine of x minus x cosine x. So what we have here, is y equals f of x minus g of x times h of x. So dy dx should be f prime of x minus g of x, h prime of x, plus g prime of x, h of x. So then we just need to know f prime of x, g prime of x, and h prime of x. G of x is x, so that derivative is 1. Sine of x is cosine of x, and cosine of x is negative sine of x. So now all we do is plug that in. G of x is x, plus g prime is 1, times h of x is cosine x. So now we distribute all of our negative signs. We have cosine of x plus x sine x minus cosine of x. Our cosine terms are going to cancel out, and we're going to be left with x sine of x. So here are our 6 trigonometric functions. We've got sine and cosine. From sine we can make cosecant, which is 1 over sine. From cosine we can make secant, which is 1 over cosine. From sine and cosine we can make tangent, which is sine over cosine. Or we could make cotangent, which is cosine over sine, or cosecant over secant. Or sorry, secant over cosecant. Something like that. Just remember cosine over sine. So what are our derivatives? Our derivatives of sine is cosine, derivative of cosine is negative sine. The derivative of secant is secant x times tangent x. The derivative of cosecant of x is negative cosecant x cotangent x. The derivative of tan is secant squared x, and the derivative of cotangent is negative cosecant squared x. We're not going to show any of the proofs for how to do these because they are really cumbersome and not necessarily helpful in understanding these. So all you need to do is just remember all of these, especially sine and cosine and tangent. The rest we don't use this frequently, but you should still know them and get used to using them. So let's do some homework problems really quick. So example, find the limit as x goes to 0 of sine of a of x over b of x, where a and b are constant. That's funny. That should just be the letter B. So what does this look like? We remember that we have the limit as theta goes to 0 of sine theta over theta equals 1. So we're going to do a little tricky mathematics, and we're going to let theta equal ax. And then we can go ahead, and we're interested now in what happens when the limit as we take theta to 0. Now we have sine theta, and we want to replace bx in the bottom with theta. So if theta equals ax, theta times b of x should be theta times b over a. Now we can always pull this out. Theta goes to 0 of a over b times sine theta theta. We can pull this out even further. A over b times the limit as theta goes to 0 of sine theta over theta. Well, we know that our second term is 1, so our first term must be a over b times 1, which is just a over b. And that's how we get that. That's how you use that tool. So let's move on to another example where we're going to do the similar thing, but not exactly the same thing. So here we still have the limit as theta goes to 0 of sine theta over theta equals 1. And what we're going to do, we're actually going to be pretty tricky here, just like we were in the last one. So we're going to say limit x goes to 0 sine of a of x over sine of b of x times x over x. And you'll all agree that I can multiply my expression by x over x because something divided by itself is 1, and 1 times something is itself. So I haven't fundamentally changed anything about this problem. But now I can write the following. Sine of a of x over x times, x over sine b of x. And now we're going to do just like we did in the last example, except I'm going to pick some different notation. I'm going to let theta equal ax and phi equal bx. And I'm going to split my limit up into 2 pieces. You'll see that in just a moment. So in this first one, as we're replacing the variable, now we want x to be in terms of theta. So it's going to be theta divided by a. And just again, we want x in terms of phi, so it's going to be phi divided by b. And we're going to pull out our constants. Nope. So I've got a times the limit theta goes to 0 sine theta over theta times 1 over b, limit phi goes to 0, phi over sine phi. Sorry that I'm going off the screen a little bit. And now we're going to do something funky. So clearly our first term is a times 1 over b, and our second term is going to be the limit of sine phi over phi quantity to the negative 1, because if I take the negative 1 of what's inside, I get what I have written previously. We can even simplify that to be a over b times, and this is our power rule for limits, we pull it all the way outside. So now we have the to the negative 1 of the limit of sine phi over phi, but we know that that goes to 0. Sorry, we know that that goes to the number 1. And 1 to the negative 1 is just 1. So hopefully that makes sense. Hopefully you're able to follow that, and hopefully it makes the first 2 or 3 questions on the homework assignment for 3.5 a little bit easier. That's it.